Hey everyone, welcome back. I'm Tim and today we're talking about power electronics. So last time we introduced the idea of this moving average. Right, basically what we're doing is we're integrating a signal of interest over some period specified here. In this case, the switching period for switch mode power supplies. Everything is divided into some kind of switching period, and we usually average over that switching period. So we integrate over the switching period and divide by that length of time to find the average over that interval. And we use this idea of the moving average to help us derive the buck converter, which you see below, right? So these are the two switching states of the buck converter. And the way we kind of derived the buck converter was trying to connect it to the idea of a voltage divider, right? So with the voltage divider, we used a resistive element to regulate an output voltage. In particular, we used a transistor as a resistive element. And last lecture, I wanted to kind of show you guys that we can use a transistor as a switching element instead. And when we use a transistor as a switching element, we're able to reduce the losses, right? We found that the efficiency of a resistive divider was related to the input and output voltages. And if we used a transistor as a switch, or if we used switches instead of resistors, we were able to avoid that loss that was associated with the resistive divider. Cool, so the way this buck converter works, just to remind you, we have two states. The first state occurs when time is between 0, and maybe I should put the greater than or equal to on the other side, so when time is between 0 and d times ts, right? So d represented our duty ratio, which was like the pulse width of the square wave that we were constructing, right? And in this case, the square wave is at the switching node, the all-important switching node. So the switching node is like the most important part of a switch mode power supply. Switching node, switch mode, it's all together, right? So the switching node is really what we should be looking at when we're trying to analyze converters, or it's an important part of what's going on in converters. So the first switching state occurs when time is between 0 and DTS, or DTSW, and the second switching state is when time is between DTSW, right, and the end of the switching period. And I should be precise with my greater than or equal to signs. So DTSW and TSW. So if we were to draw the switching node as a function of time, draw a graph as the switching node as a function of time, it would look something like this. So again, we divide time up into switching intervals, switching periods, right? So we have TSW, 2TSW. And within each switching period, we subdivide, right? So there are two subintervals. The first subinterval is when Q1 is on and Q2 is off. And the second subinterval is when Q1 is off and Q2 is on. So when in the first switching state, the Vx node is equal to the input voltage, Vbat. And in the second switching state, Q2 is on, so the Vx node is equal to 0. And in this way, we generate a square wave. And we found when we applied the moving average to the square wave, or the moving average of this square wave, turns out it's equal to d times Vbat. And after the switching node, we placed a filter which eliminated the high frequency harmonics, the high frequency content of this square wave, and just left us with the DC. And the output of that filter is the output voltage. So in other words, if the average of the Vx node is d times Vbat, then that's exactly what the filter gives us. It gives us the average at the output. So that means that Vout, the average of Vout, is equal to V times D bat, D times V bat, or the battery voltage. And as a result, we found that the conversion ratio of the buck, or the ratio of the output voltage to the input voltage, is equal to D. Cool. So basically, we can control the output voltage by varying the pulse width of this square wave. Right? So we have this controllable output voltage, but instead of varying a resistance, we vary a pulse width. Great. I just wanted to note for you guys, just to remind you, Q1 and Q2 can never be on at the same time. I hope you're thinking, why? Why can they not be on at the same time? Well, if they are on at the same time, basically what we get is a short. We short the input to ground, right? And that's bad. That's just wasting current, basically. Wasting power. So, never can we allow Q1 and Q2 to be on at the same time. Awesome. So yeah, that's basically what we just did last lecture. Just a quick reminder of what's going on. Today, I wanted to introduce the idea, or several ideas. The first one I wanted to introduce is the idea of steady state operation. And this is a very important concept. It's important because this is where most of our analysis will take place. When we analyze power converters, or switch mode power supplies, whatever you want to say, we typically assume they are operating in steady state. And it turns out this assumption greatly simplifies the analysis and enables us to understand what's going on better. So maybe I should define what steady state operation is. Well, first, the way I want to introduce it is that steady state operation is kind of in contrast to transient operation, you could say, or it's in contrast to transients. In contrast, and the reason I bring up the idea of transient operation, or a transient occurring, is because you're probably already familiar with what a transient is, right? So maybe in your circuit theory class that you've taken before, you might have encountered something like this, where you have a switch, a resistor, and a capacitor, right? Or a resistor and an inductor, or a resistor, inductor, and capacitor, right? And maybe you were interested in finding the capacitor voltage as a function of time. And you might have had some initial conditions, right? So maybe at time t equals 0, the capacitor voltage is 0. There's some R, there's some C, and also at time t equals 0, the switch closes. And it was your task to find the capacitor voltage as a function of time. And if you were to solve this, and I'm sure you did solve this, if you were to solve this, I'll do it in red. If you were to solve this, what you would find is that the capacitor voltage looks something like this. Right, so again, it started at 0, and then it slowly rose up until it reached some maximum value, the final value, right? And the final value, in this case, is the input voltage, which I've labeled Vg. And the shape of this waveform, it turns out, or the function which describes this waveform, looks something like Vg times 1 minus e to the minus t over tau, right? I hope this looks familiar to you, right? Tau is like the time constant, tau is equal to r times c. And if you vary the resistance or the capacitance, somehow it takes longer or shorter for the capacitor voltage to reach its final value. And this is, by definition, a transient effect, right? What you're doing is you're changing the state of the circuit, and for a portion of time, the voltages and currents in the circuit are varying. Eventually, that variation ceases, right? Eventually, after some long period of time, that variation in the voltage of the capacitor or the current through the capacitor stops changing, right? It ends up just being a constant value, right? So, in other words, transient operation, or a transient, is when the signals, let's say the voltages, the currents in a circuit, are varying. Maybe this is a little bit imprecise because obviously if you have an AC circuit, the voltages and currents are always varying, but in a sense there's also some kind of steady state operation in those contexts as well. What I'm referring to here is that they're varying towards some kind of steady state value. And I'll indicate by saying they're varying and tending towards a final value. Or a final, end of the road, right? They're going towards something. And what they're going towards, especially in this circuit, right? The thing that they're going towards is the steady state, right? The steady state of the circuit is the current flowing through the circuit, right? So you can imagine there's some current flowing through here, I, C of t. The steady state they're flowing to, or they're going towards, is when the current is zero. The current going through the cap is zero, and the cap voltage is Vg. So that's kind of the steady state for this circuit, right? There is some transient going on, and then that slowly settles out, and the signals stop varying in the circuit. Okay, so that's for a conventional RC circuit or LR circuit or whatever, right? You close a switch once. But in this context, right, in the switch mode power supply context, we're constantly switching between two states, right? The signals are never actually steady. So what does steady state mean for switch mode power supplies? Okay, well, I hope you've been, thinking about it by yourself, taking some time to mull over what's going on. But I'll just give it to you. I'll just give you what steady state actually means for switch mode power supplies. And in a kind of convoluted way, maybe it's a vague kind of description, but we'll look at it deeper. Steady state in switch mode power supplies occurs when the voltages and currents of the circuit begin and end each switching cycle with the same value. So if this condition holds, if the currents and the voltages, they all start the switching cycle at some value and then end at that same value, then the converter is operating in steady state, right? So it seems kind of weird that this is the same idea as what we described before, right? How is this like this voltage here? How is the voltages and currents starting and ending the switching cycle at the same values, the same as, when the capacitor current stops or it reaches the final value? How is that the same concept? Well, let's look at a waveform, right? Let's imagine we have some inductor current, and this inductor current is in steady state. What does that look like? So I'll just say it's IL of t. This is a switch mode power supply, so we're dividing time into switching periods. And I'll just draw 2 for now. So let's say that the inductor current starts at some value. Starts at I1. In the first subinterval, if we go back, in the first subinterval, well, who knows what happens? A bunch of things could happen. I mean, most precisely, what is happening is that we're applying a positive voltage to the inductor, right? If we imagine there's some VL of t, right? We're applying a positive voltage to the positive terminal, and there's some smaller voltage, right? Because V out is always less than V in at the negative terminal, which means that the derivative of the inductor current is some positive value, which means the inductor current is increasing, right? So in this first subinterval from 0 to dTSW, the inductor current rises up. Who knows what the shape is? I'll just draw it like this, right? And eventually it reaches some new current, which I'll call I2. Then, in the second switching state, the inductor current has a negative voltage applied to it, right? There's 0 at the positive terminal of the inductor, and there's some positive voltage at the negative terminal, which means that the derivative of the inductor current is negative, which means that the inductor current is decreasing. So, again, we're assuming this inductor current is in steady state. So that means that at the end of the switching cycle, the inductor current is going to return to the same value it was before, right? It's going to return back to I1. Right? So that's what the first switching cycle looks like. And now consider the fact that when we get to the next switching cycle, if we start this again, we have the same initial condition for this state, right? The inductor current is back to the same current it was before. And if you remember something about differential equations, right? Existence and uniqueness or whatever, for some initial condition, if you allow time to evolve for a specific differential equation, it's always going to reach the same values, right? It's deterministic. It's not some random event that's happening. If you start it the same way and let the differential equation evolve with time, then after a specific amount of time, that differential equation is going to yield the same answer, right? So if we go to the next switching cycle, we've started this state, we've started this subinterval with the same initial condition. It's the same differential equation, so it's going to go back up to the same current, right? It's going to go back up to I2. And excuse this drawing, but trust me, it's going to be the same, right? So this is what steady state means. We're going back up to I2. And again, we get to I2. We're in the second subinterval. Again, we go back to the same differential equation, right? This is the same differential equation as the previous cycle. We have the same initial condition for this subinterval. So that means that this current should go back down to the same value, right? Again, this is in steady state. We are assuming that this is operating in steady state. It means that the beginning and end of each switching cycle have the same value. So what does this look like, right? What it looks like, I mean, each switching cycle has the exact same waveform in it, right? And if it's in steady state forever, then the next switching cycle will also look the same, and the previous switching cycle will also look the same. So by assuming we're operating in steady state, one switching cycle looks identical to the next, right? So the averages look the same, the waveforms look the same. So you could say, right, one thing you could say, you can notice that the average of this inductor current for, say, the first switching cycle, I'll start it at t equals 0, right? If we average over this first subinterval, if we're in steady state, it's equal to the average over the next subinterval, right? Starting at TSW. And it's equal to the next one, right? This goes on forever. If we're operating in steady state, the averages of each switching cycle are the same. And maybe even more surprisingly, maybe not surprising, but it's also saying that at any given point in t, or at any given point in time, the inductor current is going to be equal to the inductor current in some other switching cycle, right? It's point-wise, right? It's not just the average is equal, it's also point-wise. Every single point of this waveform is identical to every single point in the next switching cycle, and the one after that, and the one after that. So steady state operation really means that in order to understand how the converter is operating, we can restrict our view to a single switching cycle. And this is kind of a powerful idea, right? We're not, looking back at this previous circuit, right? There's two states. The voltages and currents can kind of take whatever values, but if we're assuming steady state, then it really restricts what possible values these currents and voltages can take. And in fact, it makes it so simple that there's only this very limited range of currents and voltages that it could take. So really, this is like a way of simplifying what switch mode power supplies look like for analysis. Okay, so next I wanted to talk about small ripple approximation. So again, this is also a tool that we're going to use to simplify how we analyze switch mode power supplies. And basically, small ripple approximation allows us to ignore small variations in signals. And this is kind of convenient, right? Because if we go back to here, if we wanted to analyze everything using differential equations, we would have to take everything into account. Any tiny variation in a signal, that would have to be reflected in the differential equation. However, if we use small ripple approximation, or if we don't consider small variations in signals, then the analysis of those differential equations, in quotes, is going to be much easier, right? Because there isn't a bunch of high frequency stuff that we have to take into account. Right? And we can do this if the variation is small relative to the DC value. And this is kind of vague, right? This isn't really the most precise definition, but kind of rule of thumb, what we can say is that typically capacitors, or capacitor voltages more precisely, capacitor voltages can have small ripple approximation applied to them. But inductor currents, not so much. And the reasoning off the cuff doesn't seem so obvious, but the purpose of these DC to DC switch mode power supplies is to produce regulated DC voltages, right? So the entire point is to produce a DC voltage. So if we're thinking about our output voltage, if it doesn't have small ripple, then we're doing something wrong, right? So the output voltage better have small ripple. So we better be able to approximate this, right? Maybe I'll just write that. So one way of thinking about it, if we're designing a switch mode power supply to produce a DC voltage, it better have small ripple, otherwise we're doing something wrong. I mean, this is kind of a hand-wavy answer, but again, we're approximating, it's already hand-wavy, right? So, give me the benefit of the doubt on this one. All right, so we can write this out. We can write out this idea of small ripple approximation in a more precise way. And the way we do that is we introduce some new notation. So, typically what we'll do is we'll refer to kind of full signals or complete signals, we'll draw it over here, as V of t. So this is a time varying signal, right? It's a function of t. So who cares what it looks like? Again, I'll assume that it's periodic in nature, right? Because it's a switch mode power supply. There's periodicity everywhere. And, maybe it has some DC value, but it's also, wiggling around. The way we kind of break up this signal into 2 bits. One bit is the DC bit, right? So one bit, which we denote with the capital letter of whatever variable, right? So if it's a current, we'll use a capital I. If it's a voltage, with capital V. The capital letter represents the DC component, right? And maybe the DC component looks like this. And then the other bit, we write with lowercase and a little tilde on top. And this is like the AC component. So we're dividing up our waveforms, our signals, into 2 bits, the DC bit and the AC bit. And again, we can kind of explicitly draw this out. So maybe we have a DC bit and we have an AC bit. So the V as a function of time isn't really a function of time, right? It's constant. And then the AC bit, again, there's no DC component of this, so it must be centered at 0. Maybe it's periodic, who knows, but I'll draw in the periods. I'll draw in the switching periods. And it varies around 0. And this magnitude, if we're using small ripple approximation, this magnitude of the AC ripple, whatever it is, I'll say it's from average to peak is delta V, is much smaller than capital V. Right? We have to assume that. So if we can kind of deconstruct signals in this way, then small ripple approximation is really just saying this time varying function of t, we don't care about the time varying part, it's just constant, right? That is what small ripple approximation is, and it turns out that this kind of really simplifies basically doing integration. If we don't have to integrate all this crazy stuff, then integrals are going to be super easy. And that's really what we're trying to do. We're trying to make integration, analysis in general, easy. That's the purpose. You don't have to look deeper than that, really. If it's making it more difficult, then maybe you're doing something wrong. But in this case, it's a good thing. Cool. So those were kind of 2 simplifying concepts that we're going to use. And the next 2 things are kind of like direct tools of analysis that will enable us to figure out what the DC voltages and currents in our circuit are. So this next one is called Inductor Volt-second balance. Okay, so right off the bat, what are volt-seconds and why are we balancing them? Right, maybe that's the first thing that's going through your head. Well, to understand what volt-seconds are, well, first, an analogy. Volt-seconds are to inductors what charge is to capacitors. So I'll just write that out. So you can kind of think about that while we write some equations down, right? So the equations are very simple, right? We can kind of think about the governing equation of an inductor, right? V L of t is equal to L dIL of t by dt. And the way we're going to think about this is by taking this derivative and turning it into a difference, right? Instead of d, the letter d, we'll use delta, right? So this is not a limit anymore. It's like an explicit difference in time and in value. So delta IL by delta t. Right? So the change in the inductor current versus a change in time, right? And if we rearrange this equation, we can see that the changes in inductor current are equal to a change in time times a voltage, an applied voltage, which I'll say as VL, over inductance, right? And I hope this looks familiar because it is somewhat familiar if we think about the equation for a change in capacitor voltage, right? A change in capacitor voltage is equal to the change in charge over C, right? So it's kind of a direct correlation, right? There's like the state variable of the component, right? I and C. There is the value of that component, inductance or capacitance, and then there's this bit of energy basically, right? So for the capacitor, it's charge, right? It's current integrated over time. And for the inductor, it's voltage integrated over time, or volt-seconds, right? So basically, this is like the unit of energy that inductors store. Caps store charge, inductors store volt-seconds. Okay, so that's really all I wanted to introduce with this slide, right? Just that volt-seconds are like charge. Now let's look a little bit deeper, right? So let's look back at the governing equation of the inductor, right? Let's write this out again. VL of t is equal to L dIL of t. And in the back of your mind, because we're assuming steady state, assume steady state for this analysis. Right, this is steady state operation is kind of like in the background of everything we're doing, right? So assumes this is steady state operation. Let's apply the moving average to this, right? Let's take a moving average of both sides of this. Or let's look at the moving average. Right, so we're averaging over a switching cycle. So if we average the inductor current over a switching cycle, I'm just using the notation. And I can pull this L out, right, because integrals are linear, so I hope this doesn't disturb you too much, but it definitely works. Right, I just applied the moving average to both sides. And let's expand this out. Let's expand the right side of the equation out. So we have VL of t, the average of VL of t over one switching cycle. And on this side we have L, and if we write this out explicitly, we get 1 over TSW from 0 to TSW. I've just assumed that we're centered at 0, or we're starting at 0, right? And we're integrating the change in inductor current over time. And I'll use a dummy variable here. All right, just to indicate it's not really the same variable. We're just integrating over something like time. Okay, so what does steady state operation mean? Why have I written it here? Why have I reminded you about steady state operation? Well, if you remember what we said before, the cycle-to-cycle average of the inductor current should be the same, right? Right, the inductor current is starting and ending each switching cycle at the same value, and point-wise, it's the same cycle to cycle. The average is the same cycle to cycle. Saying that in a different way, the average change in the inductor current over one switching cycle should be 0, right? If it doesn't increase, if the average doesn't increase or decrease after a switching cycle, then the average change in inductor current should be 0 over one switching cycle. And what is this thing right here, right? This is the change in inductor current, right? The derivative is the change in inductor current. In inductor current. And this average, we're averaging the change of the inductor current. So the average change in inductor current is 0, right? Just from what steady state operation is, the average change in inductor current must be 0. So what does that mean? It means, I'll just write this out in the really nifty way it's written out, the average change in inductor current over one switching cycle is 0 if we're in steady state. If we're operating in steady state, the average of VL of t is 0. The average volt-seconds applied to an inductor over one switching cycle is 0. So this is like a really powerful tool, right? We can just look at the voltages applied to an inductor and know somehow they equate to 0. When you sum them up, whatever is applied to an inductor is 0. So looking at inductors in switch mode power supplies tells us something about voltages. Voltages with an E at the end. Voltages. So we're going to use this like every circuit you look at. You're going to apply this. You're going to apply IVSB almost no matter what. That should be like one of the first things you do. You break it down and you apply IVSB, and it tells you something about how this thing operates, what the DC voltages are in the circuit. Right? So get this in your head. The average volt-seconds applied to an inductor in steady state is 0. And written in this really cool way, it's a one-liner. Super, super cool. Okay. So that's IVSB. Next is capacitor charge balance. And this is almost identical. In fact, it's identical up to what the symbols you're using look like, right? It's completely the same, right? If we think about the average change in a capacitor voltage is equal to the change in charge of the capacitor over C, right? So again, this is like, if I'm bringing it back around, the charge is like the volt-seconds of the capacitor, right? The charge of the capacitor is the volt-seconds of the inductor. Blah, 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 blah. Cool. So, really the derivation is identical. Derivation of this is identical. So I hope you're not too scared if I just jump right into it, right? So we can start with IC of t is equal to C dVc of t by dt, right? I hope this is familiar to you, right? We look at the moving average. Moving average. Again, we're operating in steady state. And I keep saying this because if you're not in steady state, this just doesn't hold. This is just absolutely not true. So we apply the moving average. The moving average of IC of t over one switching cycle. Again, we can pull out the C is equal to the moving average of the derivative of the capacitor voltage over one switching cycle. Writing this out explicitly, right, gives us C over TSW from 0 to TSW of the average, or the change in the capacitor voltage over time, right? And again, if we're in steady state, the average value, or the average value of the capacitor voltage should not change cycle to cycle. In other words, the average change of the capacitor voltage over one switching cycle is 0. So again, that means that this integral, if we're operating in steady state, must be 0. The change capacitor voltage averaged over one switching cycle is equal to 0. And again, if you write this out in this nice way, IC of t over one switching cycle is equal to 0. This is capacitor charge balance. And again, what we're saying is that looking at capacitors tells you something about currents. This is kind of the, not the opposite, but the complement to IVSB. So if a cap voltage stays the same, it means the amount of charge you put in and the amount of charge you take out is 0 over one switching cycle. So the amount of current you put in and the amount of current you take out is 0 over one switching cycle, right? That's basically what it's saying. And again, this is something you're going to be using all the time. Literally every time you look at a circuit, this is a tool you're going to use. So now we kind of have the ability to analyze circuits. Now we have a plan of attack. So, step 0, right? Just the step that is underlying basically all of this analysis. We're assuming that the converter is operating in steady state. Have to assume this, otherwise IVSB and CCB don't hold. Next, you redraw the converter in each switching state, right? Because in one switching state, you might apply one voltage or one current, and in the other, you might apply a different voltage or current. So you have to redraw in both switching states. You write the voltages and currents seen by the inductors and capacitors, and we'll also do the input source in each state. Okay, so we have to know like the values of the voltages and currents applied. Then we apply IVSB and CCB, right? So we average the inductor current over time over one switching cycle, and we average the inductor voltage over one switching cycle, and we average the capacitor current over one switching cycle using small ripple approximation to generate a system of equations. Solve the system of equations to find the average output voltage, inductor current, input current, all that stuff. And the amount of equations will work out, right? So you won't ever end up with a situation for most converters where you have too few equations and for not enough variables. For every variable you need, you'll have some kind of equation to derive that. So this is the system you should do every single time. Every single time you get a converter, this is what you do. Assume steady state operation, redraw the converter, write the voltages and currents, apply IVSB and CCB, and then you just solve it, right? That gives you the DC voltages. And really the challenge comes with practice. You just have to get used to writing down the equations and understanding what the voltage is, what the current is. It just comes down to practice. So, do as many problems as you can, and you'll get more comfortable with doing this, and it'll become easy. And eventually you'll just be able to see what's going on, right? Without even necessarily writing explicitly all the equations. Let's do an example. Let's kind of get some experience under your belts. Okay, so we're going to look at a buck. And typically what questions will give you is they'll give you an input voltage, typically referred to as VG, generator voltage, whatever. They'll tell you what the desired output voltage is and maybe a load current. Maybe it'll be I. Sometimes it might be like R load, like what we looked at before. But again, from R load, you can just figure out what I is or vice versa. These are kind of interchangeable. It could be I, it could be R. No big deal. Right now, we don't need to worry about what L and C are. But eventually, you might see like you want the peak-to-peak inductor current, the change in the peak-to-peak inductor current to be like 20% of whatever, the average, right? Something like that. You might get some more things, but right now we're just starting with the DC solution to this converter. So this is all we're given. We don't even have switching frequency, right? It's just the input voltage, the output current, the output voltage. From this, we can figure out what D should be, basically, right? So let's do it. We split it up. We draw the converter in two switching states. We're assuming steady state. And maybe a partial step that we can do before we write out the voltages and currents is to just specify what direction the voltages and currents are, right, in each switching state. And for this, you have to be consistent, right? If you put the plus here, you better put the plus on the same side of the same component in the other state. You can't switch it around. It will screw everything up if you switch it around. So just be consistent and you'll be fine. All right. So what I'm going to do is draw the inductor current voltages in red. So this is VL applied in this direction. And according to passive sign convention, right, this is a passive component. If the voltage is specified in this direction, we can say that the inductor current flows in this direction, right? It flows into the positive terminal of the inductor. And again, we have to be consistent. IL of t flows in this direction. I'm excluding the of t's just to make it a little bit faster. Okay, so that is what the inductor voltage is, the inductor current, and we also have to think about the capacitor voltage and capacitor current. So the capacitor voltage is kind of easy, right? The capacitor voltage is the output voltage, but for argument's sake, I'll just write it out explicitly, VC. And the capacitor current, again, passive sign convention, flows into the positive terminal, right? So IC flows this way. And similarly over here, VC and IC. And we also want to think about the input current, right? Sometimes it's important to think about input current. I'm just going to get you started off on the right foot by suggesting that we look at the input current now, right? So the input current, I'll just call it IG. And IG. Again, passive sign convention, this is a source, right? This is an active, this is something that's providing power. So current flows out of the positive terminal. I've just again, you could choose these arbitrarily. You just have to be consistent. If you get a negative sign where you don't expect one, it just means that your initial assumption was incorrect. Okay, so here we go. Let's get started. Now we have to, again, step 2 is to figure out what the voltages and currents actually are in each switching state. So this occurs from 0 to DTSW. And this occurs from DTSW up to TSW. VL of t in the first state is equal to, well, the positive terminal sees VBAT, and the negative terminal sees Vout. So it must be VBAT minus Vout, or VC, I should be more explicit, VC of t, right? So this is a time varying signal. We haven't yet applied small ripple approximation, VC of t. And maybe I can even be nicer and use the same color, right? To make it look more, to allow your eye to latch on to what's going on. VC of t. Okay, in the second switching state, what's going on? Well, VL of t. Now the positive terminal sees 0 volts, right? Because Q2 is on, right? So you can say it's 0. And the negative terminal sees, again, VC of t, right? V out. So minus VC of t. And again, I've drawn plus minus VC over here, but just remember it's across this capacitor, and this capacitor is at the negative terminal of this inductor, right? It's connected right over here. And that's what you should be focusing on. Cool, so that's the inductor voltage. Now let's look at the capacitor current. IC of t. All right, in the first interval, we have to inspect this node. So what's flowing into and out of this node? Well, we have IC flowing out of the node, and I'll say that's a positive sign over here. We have IL flowing into the node, which I'll say is a positive sign in this direction, right? Oh, it's over here, right? So this is IL of T. So IC of T is IL of T. And then we have V out over R load flowing out of the node. This is the output current, right? The current flowing to the load. And maybe I'll use yellow. So we have I out flowing out of the node. And I out is equal to, in this case, V out or VC of T over R load. Right? In the second subinterval, IC of T is equal to, well, IL is flowing into it, and VC of T over R load is flowing out of it again, right? This is I out again. So it's the exact same expression. This node has not seen any change from state to state, so it's identical to this. All right, we're almost there. Or at least we're on step 1. Still on step 1. Cool, so now what we can do is we can think about what signals we can apply small ripple approximation to. Well, again, just the rule of thumb we had before was that capacitor voltages, because we expect voltages to be constant, we can apply a small ripple approximation to them. So we see VC of T here, we see VC of T here, VC of T here. So we can apply small ripple approximation to basically all of these equations. We cannot apply small ripple approximation to IL of T, right? We're just assuming off the bat that it doesn't really make sense to apply small ripple approximation to inductor currents because the ripple on inductors is typically large. So if we apply small ripple approximation, we get that VL of T in the first subinterval is equal to VBAT minus V out, right? So to be more explicit, the capacitor voltage is equal to the output voltage, right? And the average output voltage is 5 volts, just this capital V out. I almost forgot to do IG. Let's do IG right now. So IG, the input current in the first subinterval is equal to, well, I mean, this is a short, it's equal to the inductor current, IL of T. In the second subinterval, the input current is equal to, well, this is an open circuit, so it must be equal to 0. Okay, cool. Super simple, right? Let's continue with this small ripple approximation. So we can apply small ripple approximation to this equation as well. IC of T, again, we can't do it to IL, but we can do it to VC. So IC of T is equal to IL of T minus V out over R load. Again, this is, in some sense, the full signal, right? IL as a function of T. Over here, well, again, VC of T, the average is the output voltage, and there's some small ripple that we're choosing to ignore. So VL of T is equal to minus V out. And if we just continue this on down here, IC of T, after we apply small ripple approximation, is equal to, again, the full signal, IL of T, minus V out over R load. Cool. And this is just 0, and, again, we can't apply small ripple approximation to IL of T. All right, so we've done the second step, right? We've applied IVSB, or at least we've written out the voltages, the first step. Now we have to write out IVSB and CCB, so let's do it. IVSB. What it says is that the average volt-seconds applied to the inductor over one switching period is equal to 0, which means if we do this integral, right, 1 over TSW, from 0 to TSW of VL of T, that should be equal to 0. And more explicitly, we can just sub in these two subintervals, right? So from 0 to dTSW, right, for this first bit, we have VL of t is equal to VBAT minus Vout. And now you see why small ripple approximation is so powerful, right? Because these are constant. By using small ripple approximation, this integral is constant, right? And for the second subinterval, so from dTSW up to TSW, it's equal to minus Vout. Again, this is constant, right? By using small ripple approximation, we've made this integral super easy, right? Because we're just integrating constants. So if we do this, if we do these integrals, we get, again, 1 over TSW is applied to both of them. So we get 1 over TSW times VBAT minus Vout times dTSW plus 1 over TSW times minus Vout times TSW minus dTSW. Almost there, right? So we can cancel out these switching periods and we can group things together, right? So we can group the D's together, or we can group the Vouts and the VBATs together. So we have VBAT times D here. And we have Vout times D, so minus Vout times D. And minus Vout times 1 minus D. Well, D plus 1 minus D, or minus D minus 1 minus D, however you want to say it, is equal to 1. Right? Which means this is equal to dVBAT minus Vout. And according to IVSB, this is equal to 0. In other words, Vout is equal to dVBAT. And this is exactly what we got before, right? This is exactly what we found before. So simply by applying IVSB to the inductor, we found what the conversion ratio was, right? It was just basically a direct calculation. So the next step after applying IVSB is to apply CCB, right? Capacitor charge balance, right? And what capacitor charge balance says is that the average capacitor current over one switching cycle is equal to 0. Right? And we can write this out explicitly, right? So all we have to do is look at 1 over TSW times the integral from 0 to TSW of IC of t dt. And again, we can evaluate this directly, right? We just have to plug in the two subintervals. So if we go back to the previous slide, we can see that IC of t in the first subinterval is IL of t minus V out of t, minus V out over R load, right? So we can just plug that in, right? So 1 over TSW from 0 to DTS is IL of t minus V out, this is where small ripple approximation comes in again, dt. And in the second subinterval, it's equal to the same thing. So I've split it up, but really you don't have to. For this particular case, you don't have to, because it's the same in both subintervals. Okay, so it's a little bit more difficult to evaluate this, right? But what I'm going to do is I'm going to split this integral up. So we don't really know what IL of t looks like, so we can't really solve the integral per se, but we can say what it integrates to, right? We can't evaluate this directly, but we can look at what it's equal to because we know CCB means it should be equal. The sum of these things should be equal to 0. So we have 1 over TSW, and I'm going to split the integral up, right? So I'm going to recombine them. So it's one single time period, but now I'm splitting up what's inside. So in one, we have IL of t, and in the other, we have V out over our load. and this is equal to 0, right? By CCB, this is equal to 0. So this we can evaluate directly because it's a constant, but this isn't. But what it does say is that after we evaluate it, after we do this, we know that the average inductor current over one switching cycle is equal to V out over R load is equal to V out over R load. So basically the average inductor current is equal to V out over R load. And it doesn't seem like that's as strong as the conversion ratio statement, but we can write, sometimes we like to write this just as the average. So even though we didn't apply small ripple approximation, what we can say is that the average, whatever the DC component is, even if the ripple is large relative to it, the DC component is equal to V out over R load. Right? And those two, so that was basically applying IVSB and CCB and solving the equations. It just happened that solving the equations was pretty straightforward, right? So now we know that the conversion ratio is D, and the average inductor current is simply the output voltage divided by the load resistance, or the output current, right? And those are kind of like the two main things that we have, right? And maybe if we want to be more explicit, we know that the input voltage is 12 volts and the output is 5 volts. So D is simply 5 over 12. The pulse width is 5/12 of the total period, the total switching period. That's what you have to set D to in order to get 5 volts out for 12 volts in. Right? And that's how you use those tools. So in this lecture, what we did was we introduced this idea of steady state, which I've written in this kind of convenient notation where basically point-wise waveforms look identical to each other, cycle to cycle, in steady state operation. The next was this idea of small ripple approximation, right? Where we can, if ripple is small relative to the average value, we can split up that signal into a DC component and an AC component and just toss the AC component away, right? And we end up with the DC, the capital letter of the signal you're interested in. We also looked at IVSB, Inductor Volt-second balance, which says that the average volt-seconds applied to an inductor over a switching period is equal to 0. So if you apply some positive voltage for some period of time, you have to apply a negative voltage in a proportionally large amount of time, let's say, right? So IVSB, the volt-seconds applied to an inductor in one switching cycle is 0 when you're operating in steady state. So these both assume steady state operation. And finally, there's capacitor charge balance, right? Which is very similar to inductor volt-second balance, right? Except it says the average charge that you apply to a capacitor in one switching cycle when you're operating in steady state is 0. So the charge you put in is equal to the charge you take out because the capacitor voltage doesn't vary cycle to cycle, right? Because it's in steady state. So with these things, with these tools, we can analyze any converter, basically. However many inductors you want, however many capacitors you want, if you just apply these things, then you can find out what the steady state, the DC solution is. So this is like the DC analysis, let's say. And next lecture, we're going to figure out how big L and C are, right? So we kind of ignored L and C this whole time, right? I wasn't really talking about what the value should be or what the switching frequency should be, but we'll see next lecture that in order to do that, we have to draw out the waveforms explicitly. And small ripple approximation is going to help us with that as well. But that's what we'll be doing next lecture. So thanks. I hope you enjoyed your time, and I'll see you next time. Any questions? Leave them in the comments below. Bye.